remind you. Regular polygon. If I say polygon's regular, you guys remember what that means? First thing, what was the definition for regular? Like, how do I know something's regular? Yeah, so if all the angles and sides are congruent, so equilateral and equiangular, then it's regular. Okay? So this could be however many sides I want, as long as the sides are the same and the angles are the same, like the interior angles. The way you find this, the formula that you use is going to involve sides that we haven't brought up yet. So there are going to be new parts of these regular polygons that we do today. One of the things is the radius of a polygon. And that might get used more for this stuff today. There's going to be another thing also that's called the apothem that is actually used in the formula when we get to it. Now, the radius part, you saw it drawn, would go from the center of the polygon to the side. Now, the way you form the center of a polygon, of a regular polygon, I mean, is you take a circle and you circumscribe that circle around the polygon, and then wherever the center of that circle is, that's where the center of the polygon is. Okay, and everything that we call a radius in a regular polygon is essentially the radius of that circle that's circumscribed around it. Okay, and just like a circle, anything that I label as a radius in a particular regular polygon is always going to have the same length. So in this case, there's 6 sides, so there's 6 radii that I'm looking at. All those radii would be the exact same length. So if you break it down even further and you look at what these radii form, they basically form isosceles triangles for each side that's there. So there's 6 isosceles triangles in this particular regular polygon. And that's just because there's 6 sides. If there were 7 sides, I'd have 7 isosceles triangles. If there were 10 sides, I'd have 10 of them. Okay? This side right here, or this, not a side, it's really radius. But this segment, it's an apothem thing. The apothem is, by definition, I think is actually the radius of the inscribed circle. Since we don't really draw the inscribed circle, it's not that big of a deal, but it's more of a, it's the distance from the center directly to the side. Okay, so wherever the center of the polygon is, if I draw a segment measuring the distance from that center to the side, which if you do distance from a point to a segment, it has to make a right angle. That's what's going to be labeled as the apothem. Now this measurement right here will get used in the formula for area of a regular polygon. Okay, that's like one of the measurements you have to know. If you look, the apothem, guys, creates 2 right triangles inside each little isosceles triangle. Which means you got right triangles, everything we did last chapter, right? The right triangle chapter, bound to apply. You might have to do Pythagorean theorem to decide. The stuff tomorrow, sine, cosine, tangent is going to come up, even though there's a distinct process to find those. But anything that we talked about last chapter can still apply. All right. The only thing right triangle-wise you'll be dealing with today is either going to be a Pythagorean theorem kind of thing or a special right triangle kind of thing. Yes, you definitely need to know that. Now, since tomorrow we're going to get into sine, cosine, tangent, one of the things you have to be able to do is find these angle measures in here. I'm going to mark them all with an X because if this is a regular polygon, all these angles are congruent to each other. Okay? Now that angle that I marked there, right, this angle right here, it's called your central angle because it's the angle at the center. Okay? If I asked you to kind of guess or figure out exactly what the measurement of that angle is in this particular shape, right? This hexagon up there. If I ask you what you think that angle would be measured, you think you can figure it out? You got what? Watch. All right, so you're telling me you do 360, 5 by 6. Why'd you pick 360? Yeah, because if you put them all together, you can look at it, guys, they make a circle, right? There's always 360 degrees in the circle. There's 6 of those angles, they're all the same, so that's why you do 360 by 6. So in this case, that central angle is 60 degrees. If I wanted to make this into a formula, central angle is always going to be 360 divided by however many sides there are. N will always equal number of sides for what we're talking about today, tomorrow, even the next one. Okay, so you do 360 divided by n. Now this is the number of sides, or the central angle, sorry. And then the other angle that you might be working with, guys, would be the ones down here. Okay, but if you remember, guys, I said that's an isosceles triangle. So if you know the measure of this angle, you can just subtract it from 180 and divide it by 2. Or you can just do 90 minus whatever half of that is. No one's going to remember that right now. All right? Yeah.
I need to say the number of angles.
5. Which is equivalent to the number of angles. They're always the same. Okay? Now, for today, with these measurements right here, angle-wise, the way you're going to see problems given to you dealing strictly with angles are like this. I want to go through this one just because the wording usually throws people, but the problems are actually real easy. You just have to be able to figure out which one would be the 360 over n and which one you would use by doing the whole isosceles triangle. Here's the thing, 2 consecutive radii. If I was looking back at that last problem, guys, 2 consecutive radii would be like there and there. If I look at these two come together and create the central angle. So what they're doing, when you see a problem like this, and it says find the measures of the angles formed by 2 consecutive radii, they're asking you to find the central angle. Okay, that's what it's asking. It's just a different way to word it. So 2 consecutive radii will create the central angle. So if I was doing this problem, part A would just be 360 divided by the number of sides. 20 gone into 20. So what's 360 divided by 20? Quick. 360 divided by 2 is 18. 0, 3. Okay, now the other one, B, that would be the thing asking you to find these angles. All right? Understanding that the 2 radii are the same. That's an isosceles triangle, right? This would be a radius. So with this one, I'm just drawing the one triangle outside of all of them, because I'm not going to draw a 20-sided polygon. And just remember, guys, it's isosceles, like I said, those are congruent angles. So if I wanted to do B, I would just take the number I found in part A, subtract it from 18, and then cut it in half. So what's 180 minus 18? 62. And then you would cut that in half because they're both the same. Okay? All right, now, and that's probably the only thing you're doing today with angle measures. Like tomorrow, you'll be using these angles to actually find the side length, right? Because you'll be doing sine, cosine, tangent stuff, and to do sine, cosine, tangent, you need angle measures. All right? Unless you just, today you could technically be doing them because there's 30, 60, 90s in here and 45, 45, 90s. So if you forgot those, You know, you can still go back and rely on the sine, cosine, theta stuff. I'm not too worried about the whole simple radical form. Okay. What it says up there, most of the thing that, the first part that I have, it says you have to be able to find the central angle, deals more with what we're doing tomorrow. Okay? In general, that formula right there, and there's an or there, or meaning they're exactly the same. It's just one thing's written out different. This formula that says area equals 1/2 AP, that's the formula that you can use to find the area of any regular polygon. Okay, it doesn't matter how many sides it is. It can be a triangle, square, regular pentagon, regular octagon, whatever. Okay? With this formula that can be used for any of them. Now, today we're going to have like specialized formulas for certain types of regular polygons. But this is the one you use every time that it doesn't fit the specialized one. Okay, now, what these are, guys, the little a, that's your apothem. Okay, and the capital P equals your perimeter. All right, and that's perimeter of the polygon, the entire thing, not just the little triangle in there, but the entire thing, all the way around. All right, and the difference between them, like the N, S, N is the number of sides, S is the side length. The number of sides times the side length is how you find the perimeter. So all this is, like this right here is essentially P, okay? That N times S thing. It's just broken down into a little bit easier way to look at it if you know like the side length given to you or the number of sides. But guys, understand, these are the same. Okay? They're exactly the same. Alright, so if you want to write them both out, that's fine. If you simply want to write this one right here, and then maybe off to the side you write, P equals NS or something like that, right? N being the number of sides, right? S equals the side length. Then at least you can have that written separately, because there are going to be problems that say find the perimeter of it. Maybe not necessarily the area, just the perimeter. Okay? But for the most part, any shape that doesn't fit into what you'll see in a second with equilateral triangles and hexagons, you're just going to have to throw numbers into here. Okay? Just making sure you understand where the numbers go. All right? The problem shouldn't be that difficult for that. So I don't care which one you memorize, which one you get down, which one you write down here. As long as if you do the one on the left, 1/2 AP, make sure you write perimeter equals NS, or number of sides, some side length, something to remind you of that as you go through. Okay, and this picture I just put up there just so you can kind of rehash, where that A is, your bottom part. Even though it's you already have it drawn out if you did the other. Okay, now, like I mentioned, there's going to be a couple of specialized formulas today, outside of this one. All right, and they're going to be for equilateral triangles and then a hexagon. In general, you'll see when we get to this stuff tomorrow, this formula can be a little bit involved. So if you can find equilateral triangles or hexagons, like if that's involved, the problem should become a little shorter for you, because there's a special formula. Okay? First one that we're going to do is the equilateral triangle, because the hexagon is built off of this. If you have the side length of an equilateral triangle, instead of equilateral triangles are technically regular polygons, right? Because they're all the angles are the same on both sides. So instead of going in and doing the 1/2 AP formula, if you know the side length, you can simply do that. Take the side length, you square it, put a square root of 3 at the end of it, and you divide that whole thing by 4. So it's side squared times the square root of 3 over 4. Okay, so if you know the side length for an equilateral triangle, you just plug it in there. Instead of going back and doing 1/2 AP or trying to draw on a height, you might not know the height, you do 1/2 base times height. It's just less work than the previous formula that you would have seen. And guys, the equilateral triangle ones where I give you the side length, these need to be in simplest radical form because the formula has square root of 3 in it. It's already in simplest radical form. Okay, there's no need to waste time multiplying that out and making it a decimal. Okay? So, if I gave you that triangle there, it's obviously equilateral, right? Because all the sides are 5. It has to be an equilateral triangle. I said, look, I want you to find the area of that. If I didn't have this formula up there, you would have had to draw in the height, find the height, and do 1/2 base times height, which is a little bit more work because that would involve the Pythagorean theorem. Whereas if you've got this formula, you just go, my side length is 5, so I know the area of that is simply going to be 5 squared, square root of 3 over 4. The only thing you have to do is square that number out, and if it divides by 4, you divide by 4. If it doesn't, you just leave it. 5 squared is 25. That's it. I'm done. Yeah. The only other thing you would have to do is if 25 divided by 4, then you would have to divide that. That's it. Like if I use 6, then it would become, like if I change that to a 6, it would be 36 square root of 34. It would become that. Okay? So these should be fairly easy to deal with. All right? As long as you have the side length. That's what I mean. Okay? All right. Now, to build onto this. Can I go past this guy? All right. Build onto this. A regular hexagon. I don't think that was. But a horrible regular hexagon. Anyway, if I had a regular hexagon, which is what we were working with in the beginning, and in the beginning of the thing where I did the center angles, you said that was 60 degrees, right? I didn't go about finding those two angles, okay? But if I did, these would both be 60. And if all my angles are 60, would you agree that's an equilateral triangle?
Yes.
Yeah. Okay, so the reason this ties into what we just did is if I drew in all my radii there, I would in essence create how many of those triangles?
A lot.
6. So I know a regular hexagon is made up of 6 equilateral triangles. So a quick way to find the area of a regular hexagon would be to find the area of one of those regular equilateral triangles and then multiply it by 6. So there's going to be a fast way to do regular hexagons if you know either the side length or the radius, because they're the same, because that's an equilateral triangle. So this measurement here and this measurement are exactly the same. Okay? So the formula for this is in essence just the equilateral triangle formula times 6. Okay, and that's just because regular hexagons are made up of 6 equilateral triangles. If I do the formula I just had up there for equilateral triangles, multiply by 6, I will have the entire area. Okay? Now, this only works for hexagons though. If it's any other shape, right, anything that's not either a triangle or a hexagon, you have to do the 1/2 AP. Okay? So make it very, very clear in your notes that this only works for hexagons. Okay? So if I gave you that problem there, I said, look, I want you to find the area of it. All right? In essence, on that picture there, 7 is the radius, which since that thing is an equilateral triangle, those are all 7. So I do have the side length, even though I just give you the radius, even though the number wasn't on the side. So all I would have to do is say, okay, I've got my side length here. I've got the S. So I can just do 7 squared, 3 over 4, and then whatever that is multiplied by 6. And when you multiply 6, right, that goes to the numerator. 6 is 6 over 1, and when you multiply fractions, you multiply numerators together and denominators together. All right, so what's 7 squared? 49. What's 6 times 49? So this becomes 294 over 4, which you really should reduce down to, run out of room, but that. The top and bottom are both divisible by 2, so you should reduce it. Although I probably would not take off if you left it there. Okay? Those are easy ones. The equilateral triangle and hexagons are easy. Now, for you guys, if I moved into some that involve the 1/2 AP thing, okay, which I'm going to do now because I'm not worried about doing another one. All right? One like this one right here, we want that's more like a 1/2 AP. I'm going to do the decagon one first. So with the problems today, when you're doing these, and they say find area and perimeter, they might just say area. You should understand, guys, it's a regular polygon, because they're going to say in the direction, this is a regular polygon, which means I'm doing that formula, the 1/2, the apothem times perimeter. Since you're not actually finding the apothem today for most of these, they're going to tell you what it is, okay? So all that you're going to have to do, if I was doing this one here, is 1/2, 19. And then for the perimeter, remember I said make sure you get perimeter equals an S. So this is the time with ones like this where I would probably just do the number of sides times side length. Okay? For a decagon, how many sides are in a decagon?
About 10. Yeah.
It's 10 years, exactly 10. In this side length, they give you. All right? So the stuff today is going to be very straightforward if you're using these formulas. Like tomorrow, we're going to have to do work to find side lengths and apothems and stuff. So that's why I said today the work seems easier than the stuff tomorrow.
Is that square and I can do that?
I'm going to do that next.
Oh, okay.
2 problems. Okay? So that all together. 1,168,1,5. All right, so that would be area for this decagon. Okay, now the reason I have that square up there, it's a square because it would be said in the direction this is a regular polygon. The one thing I want to point out is like a square is technically a regular polygon, so I could use that formula there. Which some people are going to do, like they're going to go, if I draw that in right there, that side right there would be my apothem. And I could use it, like I could find it, right, because it's a square makes a 45, 45, 90 right triangle, so I could go and find that if I wanted. But here's the thing, a square, I mentioned it yesterday, right? I said a square is a rhombus, correct? So I had a formula yesterday for a rhombus, right? Yesterday for a rhombus we had 1/2 d1 d2, correct? If I extended that out and actually created a diagonal, how long is that part right there? 6. So the entire diagonal is how much? 12. If I drew in the other one, it's the exact same thing? Yeah. You got a square, guys, you know the diagonals, just do this for me. Like, I know the reason this would be in here is and if you looked at the work, they would do this stuff over here, it's not a need to. Though. It really is not a need to. Okay? Try and figure out which formula works the easiest. This would be the easiest one to do. As long as you recognize things like, oh, the diagonals of the square are the same, and that's halfway point there, so the other one's the exact same measure. Right? Which that would be 6 times 12 is how much? 72. Okay? Alright, so the ones that aren't equilateral triangles and hexagons, you're doing this one. Okay? Alright, so here's what I want you guys to do. In the book. No problem. Alright?
Yeah,
If you don't see them, guys, all the answers up there are correct. This one should have been 2475. This one was 292.4 square centimeters. 17 right there is 486 square to 3 square feet. This one was 16 square to 3 squared, and this one was 54 square to 3. Just that one.